The most powerful solar storm in the last 2 decades recently hit Earth, creating stunning displays of auroras, often known as the Northern and Southern Lights. This event was caused by a group of sunspots about 16 times the size of Earth. They released several X-class solar flares and coronal mass ejections directly toward our planet. These solar emissions led to severe geomagnetic storms ranked at the highest intensity level of G5, marking the most intense storms since the 2003 Halloween storms. As a result, the colorful auroras were visible much farther south than usual, with the northern lights seen as far south as Florida and Mexico, and the southern lights visible in countries like New Zealand, Australia, Chile, and Argentina. The recent solar storms have affected technology in space and on Earth. Elon Musk noted that the Starlink satellite service was experiencing issues due to the storm. He wrote on the social platform X that its satellites were under a lot of pressure, but holding up so far. The storms also disrupted power grids, GPS systems, and high-frequency communications in certain areas. These events suggest that the solar maximum, a period of peak solar activity in the Sun's 11-year cycle, might arrive earlier than anticipated. As the Sun's magnetic field flips, we can expect more geomagnetic storms in the coming months. While these storms could provide more spectacular displays of auroras, they could further disrupt radio communications and electrical infrastructure. So, what really happened on the surface of the Sun that caused the geomagnetic storm? How did it create such a stunning display of light 150 million kilometers away? Finally, and most importantly, what will happen when the sunspot group faces our planet again after 2 weeks? Before moving ahead, make sure to subscribe to our channel for regular space updates. The reason behind the recent solar storm is the sunspot group named AR3664. Sunspots are temporary dark areas on the Sun's surface, looking darker because they are cooler than the surrounding areas. The temperature in the center of a sunspot is between 3000 and 4500 Kelvin, much cooler compared to the surrounding area's temperature of about 5800 Kelvin. The AR3664 cluster rotated into view of Earth a few days ago. At that time, it looked fairly normal, but then it grew quickly to become 16 times as wide as our planet, spanning 200,000 kilometers or 125,000 miles. It became one of the largest sunspots of the current solar cycle. NOAA's Space Weather Prediction Center issued warnings of increased solar flare risk from AR3664 at the beginning of the month, and the dark patch on the Sun lived up to its expectations. AR3664 emitted a total of 75 M-class flares and 10 X-class flares within a week, accounting for 50% of the X-class flares this year. A solar flare is a sudden, localized, and intense burst of radiation on the Sun, resulting in a brilliant flash of light across various wavelengths. They can last from minutes to hours and contain tremendous amounts of energy. The light emitted from these flares reaches our planet in 8 minutes and 20 seconds. Flares are ranked by their strength. B class is the smallest, followed by C, M, and then X, the most significant. The scales differ in strength by a factor of 10. Each class is further divided into a scale from 1 to 9. C-class flares are generally too weak to affect Earth significantly. However, M-class flares can cause short-term radio blackouts at the poles and minor radiation storms, posing potential risks to astronauts. Most people get confused between a solar flare and a coronal mass ejection, or CME. A CME is an immense cloud of magnetized particles hurled into space from the Sun. These eruptions occur when the Sun's magnetic fields explosively realign, propelling solar matter into space. CMEs travel at speeds exceeding 1 million miles per hour and can take up to 3 days to reach Earth. Unlike solar flares, CMEs are massive fans of gas swelling into space. When a CME interacts with the Earth's magnetic fields, it creates currents that drive particles toward Earth's poles, leading to the formation of auroras. In essence, while both solar flares and CMEs are born from the Sun's magnetic field realignments, they emit different things, look different, travel differently, and have distinct effects on near planets like Earth. Solar flares manifest as bright flashes of light, while CMEs appear as enormous clouds of magnetized particles moving through space. The solar activity began to escalate on May 3rd with the observation of an X-1.6 solar flare. Within the next 48 hours, 2 additional X-class flares were detected. However, the situation intensified the following day when the sunspot region emitted an even larger X-4.5 flare, unleashing tremendous energy. The first coronal mass ejection was then observed departing from the Sun on May 6th. A couple of days later, on May 8th, another CME was spotted following an M8.6 flare. Then on May 9th, 2 X-class flares resulted in 2 more CMEs. By May 10th, 4 CMEs were traveling toward Earth. Scientists believe the last 3 CMEs combined into a single larger event known as a cannibal CME due to their varying speeds and overlapping trajectories. When a CME reaches Earth, something interesting happens. The Earth's magnetic field deflects the solar storm. The magnetic fields couple together and create a funnel where the gas streams down on the day side of the pole. This results in the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and the gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora. Auroras are often thought of as green, but when they are especially energetic, they can light up the sky with huge red glows. The color differences are due to the types of particles involved and the altitudes where these interactions occur. Blue and purple auroras are seen when solar particles interact with molecular nitrogen up to 62 miles or 100 kilometers. Green auroras are created when these particles interact with oxygen at altitudes between 100 and 300 kilometers, or about 62 to 186 miles. However, the striking red auroras we sometimes see occur during intense solar storms when these interactions happen with oxygen at higher altitudes, between 300 and 400 kilometers. Additionally, for red auroras to be visible to the naked eye, they must be at least 10 times brighter than the green auroras. Geomagnetic storms can have significant impacts on our electrical power grids and satellite infrastructure. During a geomagnetic storm, geomagnetically induced currents, or GICs, can flow through power transmission lines and transformers. This can cause transformers to become saturated and overheat, leading to various electrical issues. Specifically, transformers may fail, protective equipment can trip, transmission lines might overload, and generators could be damaged. In severe cases, these issues can result in large-scale blackouts. An example of this occurred in 1989 in Quebec, Canada, where a geomagnetic storm left 6 million people without power for 9 hours. Then in October 2003, the Halloween storms caused widespread satellite and communication disruptions, as well as power grid issues in Sweden. In 2022, a flare from the Sun resulted in the loss of 40 newly launched Starlink satellites. Currently, the sunspot group known as AR3664 has moved behind the Sun's disk, making it temporarily invisible from Earth. This means that any solar emissions from this group will not affect our planet for the next 2 weeks. However, AR3664 is expected to reappear and face Earth again in 2 weeks. Based on past behaviors observed in sunspots, there's a possibility that this group could remain active once it becomes visible again. Just before it rotated out of view on May 11th, AR3664 produced significant solar activity, including an X1.8 and a much larger X5.8 flare, the latter of which was associated with a CME. This activity suggests that AR3664 could still produce more solar flares in the future, and indicates that its cycle of activity isn't over yet. AR3664 is no ordinary sunspot. It's so big that it can be seen from Earth without magnification. However, do not attempt to look at the Sun without a solar filter or eclipse glasses. The size of AR3664 is comparable to the sunspot that caused the Carrington event in 1859, the most intense geomagnetic storm on record. The storm associated with the Carrington event caused sparking and fires in telegraph stations. and auroras were visible as far south as the Caribbean and Mexico. In 1859, the most advanced electrical technology was the telegraph system. Today, however, our society heavily relies on satellites and various technologies that need stable magnetic environments to function correctly. This dependence makes us more vulnerable to the effects of significant solar activity, such as that exhibited by sunspots similar to AR 3664. The increased reliance on electricity and emerging technology in today's society means that any disruption could lead to trillions of dollars in monetary losses and pose risks to life dependent on these systems. The potential impact of a Carrington-class event today has been estimated to result in damages ranging from $0.6 to $2.6 trillion in the U.S. alone. It is crucial to recognize the threat posed by extreme solar storms and take proactive measures to protect our technology and infrastructure against the potential devastation of such events. The solar storms we experienced in May 2024 suggest that the solar maximum, along with the flip of the sun's magnetic field, may occur sooner than anticipated. We've created a detailed video that explains everything you need to know about the solar cycle and its impacts on us. Be sure to watch it to understand it thoroughly. And if you learn new things from this video, please don't forget to like it and subscribe to our channel for more updates. See you in the next one.